This is the first of two lessons on implicit differentiation. This is a new topic for those of you that are on Kairos this week, and it starts off by looking at the way that most of the functions we have been written basically in terms of x, or like as an f of x. What I mean is that it's always y is equal to something with x on one side. So if you look at this first example, we have a y equal to 10x squared over x cubed plus 1 that has y on the left and x on the right. That's what we call explicit. In other words, it's clean. It's function style. I plug in an x, I'm going to get a y out on the other side. So is this next one. F of x is equal to tangent x sine 2x plus 1. If I plug in x on one side, I'm going to get f of x out. And finally, even if it's z of x, it's still y on one side, x on the other. These equations define y explicitly. But if y is a differentiable function of x, and instead of having a formula, we're given an equation with x's and y's on both sides, one that's not easily solvable for y, we call that implicit. This is defined implicitly. Basically, the best and only way to graph this is to plot a series of ordered pairs, or to have some knowledge about how the graph works. So we're going to do a technique to take a derivative of that. Sorry, I got interrupted. So this technique of implicit differentiate lets us find the slope of the tangent line when the equation can't be solved for y. Like this equation right here really can't be solved for y. It avoids trying to solve it for y, even complicated ones. It lets us find the rate of change. Remember that the slope, rate of change is essentially a slope of any point without solving for y. And it lets us compute dy dx, which is a formula for the slope of the tangent line. So here's an example. If I start with x squared plus y squared is equal to 9, you should recognize that that's the slope of a circle. So essentially what I'm going to do is I'm going to take the derivative of both sides. Now, since we're going to find y prime, we're finding dy with respect to dx. So a few things are going to hold true. The first thing is that the derivative of x is 1. But the derivative of y is y prime. We've actually done this before. And then other than that, we're just going to use chain rule a lot. So watch how I do this. I'm going to take this. This is going to be really easy, I promise. I'm going to take this and I'm going to go, let's see, we're going to take this, we're going to use chain rule on this. I'm going to look at the derivative of the inner, which is 1. Then I'm going to do the derivative of the outer, which is 2x. I know that we've taken the derivative of x squared before, but I want you to compare it to this next one. Derivative of y, we're going to say is y prime. And then the derivative of the outer is 2y equals, and then be really careful because the derivative of 9 is just 0. So if I clean that up, I actually have 2x plus y prime 2y is equal to 0. Then you simply solve for y prime. You get y prime is equal to negative 2x over 2y, or negative x over y, and I have it. There's the formula for the slope of the tangent line. Now, a second way that I'm just going to mention, but we're not going to use it a lot to do this, is actually to say that the derivative of x is dx, and the derivative of y is dy. This is actually a more correct way to do it, but they're both fine. So what I end up with is, when I take the derivative, is x squared is 2x dx, y squared is 2y dy equals 0. And I'm going to end up with the same result when I solve it for dy over dx. But I kind of like our way better because, in essence, we already have everything divided through by dx, and we're solving for y prime, which is dy over dx. So let's try a couple more of these. Let's go over to number 2. I'm going to take the derivative of this, and it says find dy dx, that's y prime. The derivative of this is 3x squared, derivative of y, 3y squared, but we have to put the y prime in for the derivative of y, is equal to 18, and I'm going to use product rule on this. First derivative of the second plus second, and the derivative of x is 1, derivative of the first. So once you've got this, all we have to do is group together the y prime terms. Well, I'm going to distribute the 18 on the right side, and actually I'm going to take one step and divide everything through also by a 3. So I just end up with x squared plus y squared y prime is equal to, and distribute the 6 xy prime plus 6y. That cuts my numbers down a little bit. Then I'm going to move the y primes to one side, so I have y squared y prime minus 6x y prime Move the non-y primes to the other side, 6y minus x squared. Then I'm going to factor out the y prime. Y prime times y squared minus 6x is equal to 6y minus x squared. And then divide both sides by what's left. I've got y prime is equal to 6y minus x squared over y squared minus 6x. And we're done. You'll notice that implicit differentiation gives us results that have x's and y's in them. If I really wanted to, I could try to substitute for some of those, but we're not going to right now, unless it becomes really easy to, and you'll see that here in a minute. So this one, if I take the derivative of both sides, I'm going to get 1 is equal to, the derivative of the inner is going to be y prime, the derivative of the outer is going to be the cosine of y. So then I get y prime is equal to 1 over the cosine of y, which I can then write as the secant of y. So that one was kind of easy. Moving on to the next one, if I take the derivative of x is 1, the derivative of sine of y, we get the derivative of y is y prime, and then cosine y. And then always remember with this, you have to use product rule. Don't ever forget product rule on that. It looks easy, it's not. Just first, well, I think it's easy. First derivative of the second plus second derivative of the first. So now we have multiple y primes. We're going to want to group those on one side. And I got y minus 1. And then I go to factor out the y prime. Cosine y minus x is equal to y minus 1. Divide both sides by y prime. I get by cosine y minus 1 x. I get y minus 1 over cosine of y minus x. Okay, next one I've got find the second derivative. So to find the second derivative, we're first going to find the first derivative. And to find the first derivative, I'm going to say y prime. Actually, I don't want to write y prime equals. And you notice I haven't been doing that because it's kind of pointless now. We just want to start taking the derivative. 4x, then minus 6y, and put a y prime in there, equals 0. And I get y prime is equal to 4x over 6y, which is the same thing as 2x over 3y. Okay, then to find the second derivative, d squared y over dx squared, what I'm going to do is take the derivative of this thing. So I'm going to go low d high, and to go low d high, I've got to do 3y, and the derivative of the high is 2. Now, that's good and clean, but then when I do high d low, I've got to worry about the y prime. High, and d low is 3, and that's y prime. Low d high minus high d low over, and if I do low low, I end up with the 9y squared. You can probably look, and I like to look and try to clean this up before we do anything else with it. So I've got d squared y over dx squared is equal to, I can divide a 3 out of everything and just make this 2y minus 2x y prime over 3y squared. Now, I really don't want to keep the y prime in there, so what I'm going to do is I'm going to substitute this in for y prime. 2y minus 2x, then I have 2x over 3y over 3y squared. So that was almost kind of pointless to try to clear the 3's, because now I just have to worry about that multiplying through by 3y. And I do want to clean this up a little bit by multiplying this and this by a 3y to get rid of that. So what I'm going to end up with is 6y squared minus 4x squared over, it's going to be 9y cubed. And that's the second derivative. Let's practice another one of those. First, find a first derivative. So 2y y prime plus, this is actually going to be 2y prime equals, derivative of 2x is 2, and then plus 1 is 0. You'll notice everything here is 2's, so I'm going to cut them out and make them all 1's. Factor out my y prime and divide what's left. So I should get 1 over y plus 1. if I write this as y plus 1 to the negative 1, then when I take the second derivative, y double prime, another way to write that, I'm going to get negative, well, let's do the derivative of the inner first. The derivative of the inner is going to be y prime, and then I have negative 1, y plus 1 to the negative 2. So we got some substitution to do. Y prime, I'm going to want to substitute with the y plus 1 to the negative 1, so that's 1 over y plus 1, times, I have a negative 1, I'll just stick that up there, and then 1 over y plus 1 to the negative third. And if I clean that up, I get, squared. If I clean that one up, I get negative 1 over y plus 1 cubed. Sorry, that should be a positive 2 down here. I see that now. There we go. Next question. Given this, find the equation of the tangent line and the equation of the normal line at this point. Well, as you guessed, we want to find a first derivative for this. So I've started doing that. 2x minus, I've got first derivative of the second plus second derivative of the first, and plus 2y y prime is equal to 0. And if I distribute the negative, I got 2x minus xy prime minus y minus 2y y prime is equal to 0. Sorry, that's a plus right there. Let's move the y prime terms on the left and keep the non-y prime terms on the right. So we should get y minus 2x. Factor out a y prime. 2y minus x is equal to y minus 2x. And I get y prime is equal to y minus 2x over 2y minus x. Whew. Okay, so it wants the equation of the tangent line at the point. Well, I should at least figure out what y prime of negative 1, 2 is. That's actually an acceptable notation to show that we're plugging negative 1, 2 into y prime. So I got 2 minus 2 times negative 1 over 2 times 2 minus a negative 1. And that's going to be equal to 4/5. So I'm going to separate this into two parts for a tangent line. I want my slope equal to 4/5. And my point is negative 1, 2, because tangent line is going to be the same. And the point of tangency is going to be the same. So I've got y minus 2 is equal to 4/5, parentheses x minus negative 1. Or y equals 4/5 x plus 4/5 plus 2. Or y is equal to 4/5 x plus 14/5. There's a good slope-intercept form for the tangent line. And then for the normal line, I want the same point but a different slope. So I'm going to have slope is negative 5/4, point is negative 1, 2, and just go from there. You can kind of pause this and work ahead if you want, save yourself some time, but I'm just going to do it. Y minus 2 is equal to negative 5/4 x plus 1, or y equals negative 5/4 x minus 5/4 plus 2, or y is equal to negative 5/4 x plus 3/4. And the last problem. Given this, same idea, so let's do a derivative. 3y squared y prime plus, this is a product rule, so first derivative of the second, 7y to the 6th y prime, plus second derivative of the first, 4x cubed, plus then 3x squared, and then equals 0. Same thing, we're going to group our y prime terms on one side. I'm going to clean this up just with a 7x to the 4th y to the 6th y prime plus, equals. Move those two over to the other, negative 3x squared minus 4x cubed y to the 7th. Let's factor a y prime out, and I'm going to do two steps in one. I'm going to factor it out and divide it over to the other side. So I should have 3y squared plus 7x squared, or x to the 4th y to the 6th for y prime. And then I want to find y prime of 1, 1, which is the whole point of this. So I've got negative 3 minus 4 over 3 plus 7. That's a little bit easier. I get negative 7 over 10. So once again, if I want my tangent line, I know that the slope is negative 7/10. My point is 1, 1. So y minus 1 is equal to negative 7/10 x minus 1. Now I'm just going to leave this here for right now because for AP stuff that's typically acceptable. For you guys, I'd want you to go ahead and give me it in slope-intercept form, but I know you can do that. I'm just going to save some time right now. Plus, as you can see, I have 10 minutes left in the period. And I got m is equal to 10/7 for the normal line, 1, 1, and we'll just put the same thing. This is a perfectly legitimate equation of the line. And that's it.